What if the universe's most profound secret isn't hidden in the brilliant furnace of a star or the sprawling arms of a galaxy, but in the precise shimmering edge of absolute nothingness? What if the key to understanding reality is written in the light that has come to the very brink of oblivion and somehow decided to dance? Your journey has brought you here to the threshold of the abyss, a place where the familiar laws of the cosmos are not just bent, but shattered into a new and terrifying geometry. The constellations of your home sky are gone, warped beyond recognition into smeared incandescent streaks. Forward, there is no destination in the conventional sense. There is only a destination in the absolute sense. A region of spacetime so violently curved that it has torn itself away from the rest of the universe, creating an inescapable pit from which nothing, not even a whisper of information, can ever return. You are approaching a supermassive black hole. The celestial sphere around you is now a distorted canvas, a maelstrom of light drawn from every corner of the cosmos, all being funneled towards a single point of infinite gravitational tyranny. Stars that should be behind you are now visible in front of you, their light captured and bent around the colossal, gravitational lens ahead, creating a ghostly warped mirror of the heavens. It's a funhouse of cosmic proportions, beautiful and deeply unsettling, a visual symphony of Einstein's most profound prediction made manifest. The silence in your vessel is absolute, yet you can almost feel the hum of space-time itself strained to its breaking point. This is the domain of the Titan, a gravitational leviathan millions or even billions of times more massive than our own sun holding court in the heart of a galaxy. Its presence is not announced by light, but by the profound and unsettling absence of it. A perfect circular void hangs in space. A hole punched through the fabric of reality. This is the black hole's shadow, the silhouette of its event horizon cast against the tortured light of the universe behind it. That dark circle, the event horizon, is the most famous feature of this cosmic monster. It is a one-way membrane, a theoretical surface that marks the point of no return. Cross it and your future contains only one possible direction inward toward the singularity. Every particle, every photon, every thought that breaches this boundary is irrevocably lost to our universe, its story terminated. For generations we have conceived of black holes as pure takers, cosmic vultures that consume without end and give nothing back. We have defined them by their darkness, their insatiable appetite, their finality. It is the ultimate prison where the warden is gravity itself and the sentence is eternal. The escape velocity here exceeds the speed of light, a physical impossibility that renders all attempts at flight utterly meaningless. It is an idea so stark, so absolute, that it has captured our imagination and our fears for over a century. We imagine a plunge into pure, featureless black, a final, silent descent into the unknown. But that understanding, that stark image of a simple fall into darkness, is incomplete. It misses the most exquisite, the most paradoxical, and perhaps the most informative feature of this entire mind-bending region. Before you reach that terminal boundary of the event horizon, just skimming the edge of forever, something extraordinary exists. It is not a structure of matter nor a cloud of gas. It is a phantom, a ghost made of pure light. A razor-thin, impossibly bright, endlessly complex ring of fire. Look closer. Within the chaotic swirl of the accretion disk, that superheated donut of doomed material spiraling inward, and just outside the perfect black of the event horizon, there is a line of pure, brilliant intensity. This is the last light you can see, the final photon you could ever witness before the universe winks out. This is the Photon Ring. It is a celestial tightrope walked by particles of light. Imagine a photon born in a star 1 billion years ago that has travelled across intergalactic space on a journey of unimaginable scale. Its path by pure cosmic chance brings it not into the black hole, nor on a course that will safely bypass it, but to a place of perfect, terrifying equilibrium. It skims the abyss at just the right distance, precisely 1.5 times the radius of the event horizon for a non-spinning black hole, where the gravitational pull is so exquisitely balanced that the photon is neither immediately captured nor allowed to escape. Instead, gravity seizes the straight path of the light and bends it into a perfect circle. The photon is trapped. It is now in orbit. not like a planet around a star held by a gentle gravitational tether, but like a race car on a banked track of pure space-time curvature forced into an eternal loop at the speed of light. This is not just one photon, it's a collection of countless trillions of them, each arriving from a different time and a different place, all captured on this gravitational precipice. Some may have been travelling for only a few minutes, originating from the nearby accretion disk. Others may be ancient wanderers, their light having left a distant galaxy, when the universe was just a fraction of its current age. They all meet here at the edge of the void, their vastly different histories converging into a single, shimmering eternal present. The Photon Ring is therefore not just a place, it is a repository of cosmic memory. It is a film reel of the universe's history playing on a loop for an audience that can never get close enough to see it clearly. Every photon in that ring is a messenger carrying a story of its origin, a snapshot of a star, a galaxy, a quasar now held in gravitational stasis. What would you see if you could get closer, if you could resolve the structure of this ethereal halo? You would witness something straight out of a fever dream. Because the light in the ring has orbited the black hole, it can show you things that are physically behind it. A photon might leave the back of your own head, travel forward a loop once completely around the black hole, and then enter your eye from the front. You would quite literally see the back of your own head. Look into the ring and you would see the entire universe reflected not once, but an infinite number of times. The light that has completed one orbit creates a faint, ghostly image of the cosmos. The light that has managed to survive for 2 orbits creates a second, fainter, more compressed image nested inside the first. 3 orbits, a third image. 4, a fourth. The Photon Ring is a set of nested Russian dolls made of pure light, a fractal boundary containing an infinite number of thinner, fainter rings, each one a more distorted and time-delayed map of everything in existence. It is the universe folded in on itself, compressed into a sliver of incandescent perfection. This structure, this delicate gravitational gyroscope, is a direct consequence of Albert Einstein's theory of general relativity. His revolutionary idea, now the bedrock of modern cosmology, reimagined gravity not as a simple force, pulling objects together, but as the curvature of a 4-dimensional fabric called spacetime. Matter and energy, he proposed, tell spacetime how to curve, and the curvature of spacetime tells matter and energy how to move. A planet orbiting a star is simply following a straight line through the curved spacetime created by that star's mass. A black hole represents the most extreme expression of this principle. It is a region where an immense mass has been crushed into an infinitesimally small point, creating a gravitational curvature so profound that it becomes a bottomless well in the fabric of reality. The Photon Ring exists at the lip of this well. It is the last stable place, the final circular path that anything, even light, can take. Any closer, and the slope becomes too steep. Any closer, and the fall is inevitable. For decades, this mesmerizing ring was purely a mathematical curiosity, a strange but beautiful prediction spun from the complex equations of relativity. It was an abstraction, a theoretical ghost haunting the edges of a theoretical monster. No one ever dreamed we could actually see it. How could you possibly image something so small, so faint and so far away, wrapped around an object that is by its very definition completely black? The supermassive black hole at the heart of our own Milky Way galaxy, Sagittarius A, is 26,000 light-years away. Resolving its photon ring from Earth would be like trying to see a single atom on the surface of the Moon. The task seemed not just difficult, but fundamentally impossible, a fantasy confined to the blackboards of theoretical physicists. It was a beautiful idea, but one destined to remain forever beyond our observational grasp, a secret the universe would keep to itself. But humanity is a species defined by its refusal to accept such limits. We are driven by a relentless curiosity, a deep-seated need to see what lies beyond the next hill, the next ocean, the next world. That same impulse that drove us out of Africa and across the globe, that pushed us to sail uncharted seas and launch ourselves toward the moon, is now driving us to peer into the very heart of darkness. We began to wonder, what if we could build a new kind of eye? What if we could construct a telescope, not of meters, but of thousands of kilometers, a telescope the size of a planet? This audacious dream gave rise to one of the most ambitious scientific collaborations in human history, the Event Horizon Telescope. By linking radio dishes across the globe from the mountains of Chile to the ice of the South Pole from Hawaii to Spain, we synchronized them to work as one single Earth-sized virtual observatory. We built a planetary eye and we turned it to the heavens, aiming it at the colossal black hole in a galaxy 55 million light-years away, Messier 87. In 2019, the world held its breath as the first image was revealed. There it was. A blurry asymmetrical ring of light encircling a dark central void. For the first time in history, we had direct visual evidence of a black hole's shadow. It was a triumph of science, technology, and human collaboration, a picture that will forever be enshrined in the annals of discovery. The image was everywhere, a cosmic donut that confirmed Einstein's theory in the most extreme environment we could find. We had seen the unseeable. Yet for the scientists who had dedicated their lives to this quest, that historic image was not the end of the journey. It was merely the beginning. Because that bright fuzzy ring that the world saw, as monumental as it was not the true photon ring. It was the heavily blurred composite light from the turbulent, chaotic environment around the black hole. The real prize, the thin, sharp, infinitely complex series of nested rings, predicted by relativity, remains hidden within that blur. Seeing that razor-sharp line is the next great frontier. It is the holy grail for black hole astronomers, because capturing it would be far more than just taking a prettier picture. The precise shape and structure of the photon ring are dictated with mathematical purity by the properties of the black hole itself. Its size is a direct measure of the black hole's mass. The subtle warping of its shape would reveal how fast the black hole is spinning, dragging the very fabric of space-time around with it, like a submerged rotating sphere dragging honey. The ring is a celestial fingerprint, a barcode that encodes the fundamental nature of the object it encircles. By studying it, we can test general relativity with a precision that has never before been possible. Does Einstein's theory hold up under this unimaginable strain? Or at this ultimate edge will we see the first tiny cracks in his century-old masterpiece, hinting at a new, deeper theory of gravity and the universe? The ring is a cosmic laboratory, a crucible where our most fundamental understanding of reality is put to the ultimate test. This documentary is the story of that quest. It is a journey to the edge of space and time, a detective story written in the language of bent light and curved space-time. We will explore the minds of the theorists who first imagined this impossible structure, and the monumental efforts of the observers who are now striving to capture it. We will venture into the violent, superheated world of the accretion disk, the chaotic engine that feeds the monster and illuminates its silhouette. And we will stand at the final precipice, gazing into that shimmering gossamer ring of light. For this is more than just a scientific curiosity. The photon ring touches upon our most profound questions about existence. It is a boundary between the known and the unknowable, between a story that can be told and one that is lost forever. It is the universe's last beautiful, defiant spectacle before the final curtain of the event horizon falls. It is the last light, and its secrets are waiting. To see it, to truly understand it, we must first build the most powerful telescope in the history of the world. And so we did. What if the universe's most fundamental constant wasn't a constant at all? What if the straight line, the very definition of the shortest path, could be forced to bend, to twist, to circle back on itself? This wasn't just a fanciful question for a young patent clerk in Bern, but a profound crack in the edifice of physics, a contradiction so deep it would demand that we rethink nothing less than the nature of space, of time, and of gravity itself. For centuries, our cosmos was a place of comforting certainty. It was Isaac Newton's universe, a grand and predictable clockwork wound by a divine hand and left to run according to immutable laws. Gravity in this majestic design was a force, an invisible instantaneous tether stretching across the void, pulling apples to the earth and holding planets in their orbits. It was a simple, elegant and powerful idea that described our world with breathtaking accuracy for over 200 years. It was also, as Albert Einstein would come to realize, profoundly wrong. The problem wasn't in the results. Newton's equations worked. They could guide a ship, predict an eclipse, and explain the tides, The problem was conceptual, a deep logical inconsistency that gnawed at the very heart of what we thought we knew. The flaw was light. According to the physics of the day, light was pure energy. It was massless. And if gravity was a force that acted only on mass, then light should be utterly immune to its pull. A beam of starlight on its journey across the cosmos should fly perfectly straight, indifferent to the colossal stars and galaxies. It passed its path an unerringly perfect line. But Einstein, wrestling with his new theory of special relativity, suspected this couldn't be the entire story. A deeper principle was at play, an idea he would later call the happiest thought of his life. It was a thought experiment of brilliant simplicity. Imagine you are in an elevator, a sealed box with no windows. Suddenly you feel your feet press firmly against the floor. Are you sitting on the surface of the Earth held by its gravity? Or are you in deep space in an elevator being accelerated upwards by a powerful rocket, the inertia of your own body creating the sensation of weight? Einstein's revolutionary insight was that from inside the box there is no experiment you could possibly perform to tell the difference. Acceleration and gravity, he declared, were fundamentally indistinguishable. They were two sides of the same coin. This, the principle of equivalence, was the key that unlocked everything. If acceleration and gravity were the same, then what happened in one frame of reference must also happen in the other. Now imagine you are back in that accelerating elevator in deep space. A mischievous physicist outside drills a tiny hole in one wall and shines a laser beam straight across. From the physicist's perspective, the light travels in a perfect line. But from your perspective, inside the accelerating box, the floor is rushing upwards to meet the light beam. By the time the light reaches the far wall, the elevator has moved up. The beam will not strike the wall at the same height it entered, it will strike slightly lower. To you inside the box, the path of light has not been straight. It has curved, it has followed a gentle downward arc, and now the stunning conclusion of that happiest thought. If you cannot tell the difference between acceleration and gravity, and if a beam of light curves in an accelerating reference frame, then it must also curve in a gravitational field. Light, even with no mass, must bend. Gravity was not a force pulling on things. It was something far more profound, far more woven into the world. Einstein had to abandon the old comfortable ideas of an empty stage on which the drama of the cosmos unfolded. He realized that space wasn't an empty container. And time wasn't the universal ticking clock everyone assumed it to be. They were bound together a single dynamic entity, spacetime. This four-dimensional landscape was the true stage of the universe, and it wasn't rigid. It was active, flexible, malleable. He gave us a new metaphor, one we still use to this day. Imagine space-time as a vast stretched rubber sheet. In a region far from any matter, the sheet is flat. An object moving across it like a marble travels in a straight line. But now place a heavy bowling ball in the center of that sheet. The fabric of space-time itself distorts, it sags, it curves. Now when you roll a smaller marble nearby, it no longer travels in a straight line. Its path is deflected by the curvature created by the larger mass. It appears to be attracted to the bowling ball orbiting it, but there is no mysterious force pulling it. The marble is simply following the straightest possible path through a space that has been warped. This was Einstein's general theory of relativity. Mass does not create a force called gravity. Mass tells space-time how to curve, and the curvature of space-time tells mass how to move. It was an idea of staggering elegance and cosmic grandeur. It explained everything Newton's theory did, but with a deeper truth. It accounted for tiny anomalies in Mercury's orbit that had puzzled astronomers for decades. And it made a series of wild, testable predictions. None was more audacious than its claim about the path of light. If gravity was truly the warping of space-time, then the light from a distant star passing close to our own sun should have its path bent by the sun's immense gravitational dimple. The star wouldn't have moved, but from our vantage point on Earth it would appear to be in a slightly different position in the sky. The effect would be minuscule, a deflection so tiny that it would be utterly swamped by the blinding glare of the sun itself. To see it to test Einstein's radical new vision of the cosmos, you would need to block out the sun's light while leaving the stars around it visible. You would need a total solar eclipse. In 1919, a British astronomer, Arthur Eddington, set out on a grand expedition to do just that. The world was still reeling from the Great War, a conflict that had pitted British and German scientists against each other. But Eddington, a Quaker and a pacifist, saw a chance not just for a scientific triumph, but for a moment of human reconciliation, a British astronomer voyaging to prove the theory of a German physicist. He led 2 teams to opposite sides of the Atlantic, one to Sobral in Brazil, the other to the island of Principe off the coast of West Africa. They were there to chase a shadow to wait for that fleeting moment when the moon would perfectly obscure the sun, revealing the stars of the Hyd's cluster, which would be positioned right beside the solar limb. The tension was immense. The photographic plates were heavy and fragile. The tropical weather was a constant threat. In Principe, where Eddington himself was stationed, the morning of the eclipse was cloudy and fraught with storms. For agonizing hours, it seemed the entire venture might be a failure. Then, just as totality began, the clouds parted. A ghostly pearlescent corona bloomed in the suddenly dark sky. Frantically, Eddington and his team began exposing their plates, capturing the faint pinpricks of starlight from behind the eclipsed sun. They were photographing the shape of space itself. Months later, after painstaking analysis back in England, the results were announced at a packed meeting of the Royal Society. The starlight had indeed been bent, and the amount of deflection was not what Newton's older ideas would have suggested. It matched the predictions of Einstein's warped spacetime almost perfectly. The headlines were sensational. "Revolution in science," one paper declared. "New theory of the universe, Newtonian ideas overthrown." Einstein overnight became a global icon. His abstract mathematical daydream had been shown to be the literal architecture of our reality. Space and time were not fixed. They were a dynamic fabric that could be bent and shaped by mass. But if the gentle gravity of our sun could warp spacetime enough to visibly bend starlight, it begged a terrifying new question. What would happen in the presence of truly extreme gravity? The answer had already been found, though few at the time could grasp its monstrous implications. In 1915, just months after Einstein published his equations, a German physicist named Karl Schwarzschild found the first exact solution to them. He did this extraordinary work while serving on the Russian front calculating complex tensor equations, amidst the deafening roar of artillery fire. His solution described the gravitational field outside a single, non-rotating, spherical mass like a star. But buried within his mathematics was something bizarre, something that seemed more like a pathology than a physical reality. Schwarzschild's equations showed that if you could compress any mass down to a small enough size, the Sun, to a width of just a few miles the Earth to the size of a sugar cube, something incredible would happen. The curvature of space-time around it would become infinite. It would in effect punch a hole in the fabric of reality. The object would collapse under its own gravity, forming what he called a singularity, a point of infinite density. And surrounding this point would be a one-way membrane, a surface of no return. We call it the event horizon. For decades, this idea was treated as a mathematical curiosity. Even Einstein himself refused to believe it could be real. The universe, he thought, must have some built-in safety mechanism to prevent such a complete and total gravitational collapse. But the math was relentless, and it led to an even more ghostly prediction, a direct consequence of light bending in this ultimate gravity well. Imagine you are watching a beam of light as it grazes past one of these hypothetical objects, what we now call a black hole. If the light is far away, its path is only slightly deflected, much like the starlight in Eddington's experiment. It continues on its journey, slightly perturbed but otherwise free. But as you aim the beam closer and closer to the object, the bending becomes more and more severe. The curvature of space-time is like a deepening whirlpool. A beam that passes too close is inevitably captured, dragged across the event horizon, and lost from our universe forever. Between the path that escapes and the path that falls in, however, there must exist a boundary. A perfect critical distance, a path of exquisite and terrifying balance. At a precise distance from the centre of the black hole, exactly 1.5 times the radius of its event horizon, the curvature of space-time is so perfectly warped that it can bend light into a circle. A photon arriving at this exact altitude, with this exact trajectory, will not escape, nor will it immediately fall in. Instead, it will be forced into a permanent circular orbit. This is the photon sphere. It is not a solid surface, but an invisible gravitational cage for light. A shell of pure energy made of countless photons, each one a prisoner of gravity looping around the black hole forever. Imagine standing on a hypothetical platform within this sphere, somehow protected from the tidal forces that would tear you apart. If you were to look straight ahead, the light from the back of your own head after travelling all the way around the black hole would return to your eyes. You would see yourself from behind. Look to your left and you would see what is on your right. The entire universe would appear distorted, wrapped around you in a kaleidoscopic hall of mirrors. Every photon here is a messenger from the distant past, captured from some long-dead star or ancient galaxy, now forced to endlessly relive its journey. It is a realm where light, the fastest thing in the universe, is brought to a standstill in its outward journey, its immense velocity perfectly counteracted by the inward plunge of spacetime itself. It is light on a razor's edge. This orbit, however, is fundamentally unstable. It is the universe's most precarious balancing act. Like trying to balance a pencil on its sharpest point, the slightest disturbance from any direction spells doom. A photon whose path wavers infinitesimally outward will be flung away, escaping the black hole's grasp to carry its story across the cosmos. A photon that nudges ever so slightly inward will lose its battle. It will begin an unstoppable spiral, crossing the event horizon and descending into the singularity, its journey finally over. The photon sphere is therefore not just a place but a process. It is a flickering, shimmering halo populated by transient light. It is the final, desperate orbit possible for a particle of light before it is either lost forever or granted a final reprieve. Einstein's theory, born in a quiet office from a simple thought about a man in a falling elevator, had led us here. It predicted a place where the fabric of reality is so stressed that it can imprison light itself in an eternal dance on the brink of oblivion. For most of the 20th century, this remained pure speculation, a ghost in the machine of relativity. It was a masterpiece of mathematics, a symphony of theoretical physics. But was it real? Could we ever hope to witness this celestial blowtorch, this ghostly halo of captured light? How do you take a picture of something that by its very nature is on the edge of the deepest darkness in the entire universe? The prediction was on the books. The challenge had been thrown down. Now the hunt for the last light you could ever see would begin. So the mathematics held a breathtaking promise. A ring of pure light trapped in an eternal, frantic orbit at the edge of existence. For decades, however, that is all it was, a ghost haunting the margins of Einstein's equations, an elegant truth written in a language no telescope could yet read. General relativity had provided the map, a stunningly precise blueprint for the most extreme environment in the cosmos, yet the territory itself remained unseen, shrouded in distance and darkness. The event horizon was by its very definition the boundary of the observable. And the photon ring, balanced precariously on that knife edge, seemed destined to remain a spectre of theory, a beautiful but ultimately frustrating footnote in the story of gravity. How do you even begin to look for something so small, so distant and so profoundly strange? How do you build an instrument capable of seeing the unseeable? For a long time, the chasm between the poetry of the equations and the hard reality of observation seemed utterly unbridgeable. We knew with unnerving certainty that these gravitational titans were out there devouring stars and shaping the destinies of galaxies. We could infer their presence from the frantic dance of orbiting stars or the colossal jets of plasma they hurled across intergalactic space, but we couldn't see their form. It was like trying to understand the nature of a whirlpool by only watching the debris circling its edge, never glimpsing the terrifying vortex at its heart. The problem was one of translation. The abstract four-dimensional space-time curvature described by Einstein needed to be converted into something we could comprehend, a two-dimensional image. Light, a picture. That transformation, that crucial leap from mathematical symbol to visual reality, would not happen in an observatory dome or at the eyepiece of a telescope. It would happen inside a machine born from the humming heart of a new kind of science. The answer began not with steel and glass, but with silicon and code. Before we could hope to see a black hole with a real telescope, we first needed to teach a computer how to see one. This was the dawn of computational astrophysics, a field that would allow humanity to conduct experiments not in a lab, but in a digital universe of our own making. The pioneer of this digital voyage was a French astrophysicist named Jean-Pierre Luminet. In 1978, armed with an IBM 7040 mainframe, a primitive beast by today's standards with less processing power than a modern wristwatch, he embarked on an audacious quest. He sought to create the very first realistic image of a black hole not as a mathematical point, but as it would actually appear to a nearby observer. The task was monumental. He had to translate the complex interwoven equations of general relativity into a language the computer could understand, a series of instructions in Fortran and punch cards. He couldn't just take a simple snapshot. A black hole's gravity doesn't just bend light, it shatters and remakes the very concept of a straight line, twisting the fabric of space-time into a labyrinth. To simulate this, Luminet had to calculate the path of every single ray of light one by one, tracing its journey backward from a hypothetical camera's film to its origin in the distant cosmos. This technique, known as gravitational ray tracing, was painstakingly slow. The computer would spend hours, even days, meticulously tracking these phantom photons as they navigated the treacherous gravitational tides around the event horizon. Some light rays originating from a star far behind the black hole would be gently deflected, their paths curved as if by a cosmic lens. Others passing closer would be captured entirely, their journeys terminating in the singularity, contributing nothing but blackness to the final image. But a special few, those arriving at just the right angle, would be ensnared in that critical region we now know so well. They would be forced into orbit, circling the black hole one, two, or many times, before a fraction of them managed to escape and reach the virtual camera. These were the photons that would form the ring. After over a year of calculations running his program night after night, Luminet finally had his result. It was a grainy black and white image composed of thousands of individually calculated points. And it was a revelation. The simulation showed not just a black circle, but a complex, distorted, and strangely beautiful structure. It revealed an accretion disk of superheated gas, the matter spiraling to its doom, which was twisted into an impossible shape by the black hole's gravity. The part of the disk behind the black hole was gravitationally lensed into a glowing halo, arching over the top. The part of the disk in front was bent into a secondary image beneath it. And critically, the simulation confirmed the lopsided nature of the ring. The side of the disk spinning towards the observer appeared intensely bright, a phenomenon known as Doppler beaming, where the light is concentrated and blue shifted to higher energies. The side spinning away was dimmer and redder, its light stretched and enfeebled by its motion. At the centre of it all was the void, the black hole's shadow, the tangible imprint of the event horizon on the sky. And nestled just inside the larger glow of the accretion disk, Luminet's simulation predicted the existence of that impossibly thin, razor-sharp band of light, the photon ring itself. It was the first visual confirmation of a century of theory. This digital ghost, conjured from pure mathematics, became our guide. It was the celestial blueprint, the treasure map that told us not only that a picture was possible, but precisely what we should be looking for. As computing power exploded through the late 20th and early 21st centuries, these simulations grew astonishingly sophisticated. Teams of scientists around the world built on Luminet's foundation, creating virtual black holes with ever-increasing fidelity. They added the violent physics of plasma, the intricate dance of magnetic fields, and the turbulent chaotic flows of infalling matter. These new simulations, running for months on supercomputers the size of city blocks, produced images of breathtaking complexity and realism. They showed us how the photon ring would flicker and warp its structure, encoding deep secrets about the black hole's mass, and most tantalizingly its spin, the degree to which the monster was twisting the very space-time it inhabited. The theory was now visible. The target was in sight. But the digital dream only served to highlight the immense, almost impossible engineering challenge that lay ahead. The simulations gave us a clear picture, but it was a picture of something incredibly vanishingly small in our sky. To understand the scale of the problem, you need to think about angular resolution, a measure of a telescope's ability to distinguish fine details. Imagine standing in Los Angeles and trying to see a single orange sitting on the surface of the moon. That is the scale of the task. That tiny, barely there speck is the apparent size of the event horizon of the supermassive black hole at the centre of our own galaxy. No single telescope ever built or even conceived could achieve such a feat. The laws of physics dictate that to get a sharper image you need a bigger telescope. To resolve an object as small as a black hole's shadow, you would need a radio telescope dish the size of the entire planet Earth. For decades, this fact alone relegated the idea of imaging a black hole to the realm of science fiction. Building such a structure was physically impossible, but what if you didn't have to? What if, instead of building a single planet-sized dish, you could create a virtual one? This is the genius behind a technique called Very Long Baseline Interferometry, or VLBI. The principle is as elegant as it is audacious. Instead of one enormous mirror, you use a network of many smaller radio telescopes, all separated by vast distances, thousands of miles across continents and oceans. You point every single one of these telescopes at the exact same cosmic target, at the exact same time. Each telescope in the network acts like a tiny isolated fragment of that impossible planet-sized mirror. Individually, each dish collects only a faint incoherent whisper of a signal, a meaningless stream of static. But the magic happens when you bring all that data together. By precisely measuring the infinitesimally small differences in the arrival time of the same radio wavefront at each station, you can begin to reconstruct the image. It's like listening to a single clap of thunder with a dozen microphones scattered around a city. From the slight delays in when each microphone registers the sound, you could pinpoint the exact location of the lightning strike. VLBI does this with light using the entire Earth as a vast optical instrument. The greater the distance between the telescopes in the array, the finer the detail you can resolve. This was the key. This was the path that could finally lead us from the simulated universe to the real one. And so, one of the most ambitious scientific collaborations in human history was born the Event Horizon Telescope, or EHT. It wasn't a new observatory built in one place, but a grand alliance, a unification of existing telescopes around the globe, all synchronized to work as one. It would become a planetary-scale eye forged from a network of antennas scattered from the bone-dry Atacama Desert in Chile to the volcanic peaks of Hawaii, from the sun-scorched plains of Spain to the frozen windswept ice sheet of the South Pole. Each location was chosen for its high altitude and dry air, essential for peering through Earth's turbulent atmosphere, which blurs and distorts the faint radio waves arriving from deep space. The technical hurdles were staggering, pushing the boundaries of engineering, computation, and global coordination. First, to stitch the signals together, every telescope in the network had to be synchronized with unimaginable precision. Each observatory was equipped with a hydrogen maser atomic clock, a device so stable it would not lose or gain a single second in over 100 million years. These clocks ensured that the timestamp on every byte of data from every telescope was accurate to within trillionths of a second. Without this level of temporal harmony, the data would be useless noise. Next came the deluge of data itself. The radio signals from a black hole's edge are incredibly faint, weaker than the signal from a mobile phone on the moon. To capture this cosmic whisper, the EHT had to record an immense amount of information, a flood of data so vast that it could not possibly be transmitted over the internet. Instead, each station recorded its observations onto stacks of high-capacity helium-filled hard drives. At the end of an observation run, these drives weighing half a ton from a single station would be physically flown by cargo plane from these remote corners of the world to two central processing centers, one at MIT's Haystack Observatory in the United States and the other at the Max Planck Institute for Radio Astronomy in Germany. The project was a logistical ballet on a global scale, where a single snowstorm in Chile or a delayed flight from the South Pole could jeopardize the entire endeavor. Everything had to work in perfect concert. The weather had to be clear simultaneously across the entire planet. The multi-million-dollar receivers had to function flawlessly in some of Earth's most hostile environments, and the atomic clocks, the very heart of the experiment, had to remain in perfect, unwavering sync. With this planetary instrument painstakingly assembled, the hunt could finally begin. But where in the vastness of the cosmos should this new eye turn its gaze? Out of the billions of black holes thought to exist in the observable universe, only two were viable candidates. Two cosmic titans that met the stringent requirements of being massive enough and just close enough for their shadows to be theoretically resolvable from Earth. The first target was the monster at the heart of our own galaxy, the Milky Way. It is called Sagittarius A, or Escar A for short. It lies just 27,000 light-years away, a stone's throw in cosmic terms. Escar A contains the mass of 4 million suns, all compressed into a volume smaller than the orbit of Mercury. Its proximity made it an irresistible target. However, it came with its own unique challenges. Looking towards the galactic centre from Earth is like trying to see a candle flame through a thick fog. Our view is obscured by dense clouds of intervening gas dust and stars which scatter the faint radio waves we are trying to detect. Furthermore, Escar A is a relatively small, supermassive black hole. Matter orbits it in a matter of minutes, not days, meaning its immediate environment is a furiously changing turbulent whirlpool. Trying to image it is like trying to take a long exposure photograph of a spinning top. The second target was a true Leviathan. Its name is M87, and it is the galactic emperor residing at the centre of Messier 87, a giant elliptical galaxy 55 million light-years away in the constellation Virgo. M87 is one of the most massive black holes we have ever discovered. It is a behemoth of almost incomprehensible scale, weighing in at 6.5 billion times the mass of our Sun. Its event horizon is so vast that our entire solar system could fit comfortably inside it. What it lacked in proximity it made up for in sheer colossal size. Its immense gravity meant that the material swirling around it moved far more slowly and predictably than at Skyrine, making it a more stable target for an image. And unlike our obscured view of the Milky Way's core, M87 sits in a clean line of sight, offering a clearer if much more distant window into its soul. These were the two great contenders, the frantic nearby storm of Sagittarius A and the distant placid giant of M87D. For years, the international team of hundreds of scientists and engineers prepared. They refined the hardware, tested the software, and ran endless simulations preparing for the moment when the telescopes, the weather, and the cosmic alignment would all fall into place. In April of 2017, that moment finally arrived. For 10 consecutive days under crystal-clear skies across the globe, the planetary scale eye of the Event Horizon Telescope opened. From Antarctica to Arizona, from the Alps to the Andes, the dishes turned in unison, staring intently at these two infinitesimally small points of darkness in the sky. They listened silently to the ancient light that had travelled for thousands and millions of years to reach them. Petabytes of data, a digital torrent of information poured onto the waiting hard drives. The observation was a flawless success. The telescopes had stared into the void. The hard drives were full. But the picture, the ghost we had been chasing for a century through the language of mathematics and the logic of code, was not yet there. It was shattered, broken into a billion pieces of raw data scattered across the globe. A planetary puzzle holding the first real glimpse of infinity, waiting for someone to put the pieces back together. And so, the vigil began. A quiet, agonizing period of waiting that settled over the global collaboration after the storm of observation. For years, the Event Horizon Telescope had been an audacious blueprint, a theoretical giant built from ambition and steel. In those few nights in April 2017, it had finally opened its composite eye, staring for 100 sleepless hours into the heart of the Virgo galaxy cluster 55 million light-years away. The signals, the faint whispers of a monster, had been captured. They were not an image, however, but a deluge of raw, uncorrelated data, a chaotic storm of radio waves recorded with picosecond precision by atomic clocks. This precious, impossibly fragile cargo was now stored on hundreds of specialized helium-filled hard drives, too vast to transmit over the internet. These were not mere data vaults. They were digital arcs, each one carrying a piece of a puzzle that had never been seen before. From the thin, frigid air of the Atacama Desert in Chile, from the volcanic peak of Mauna Kea in Hawaii, from the icy plateau of Antarctica, and from the mountains of Spain and the deserts of Arizona, the drives began their pilgrimage. They were flown by commercial jet, carefully hand-carried by scientists who understood they were holding a fragment of a new reality. The journey itself was a testament to the scale of the challenge. A single drive slipping through airport security, a customs delay, or a catastrophic failure could have created a permanent hole in their virtual telescope mirror, a blind spot in their vision of eternity. every byte of the 5 petabytes of data, enough to store the entire selfie collection of 40,000 people for their whole lives, or listen to MP3 quality music for 5,000 years, was utterly irreplaceable. This was the first physical reunion of information from a telescope the size of a planet. The destination for this global harvest was not a single gleaming laboratory, but the Max Planck Institute for Radio Astronomy in Bonn, Germany, and the MIT Haystack Observatory in Massachusetts. Here they were fed into the metallic heart of supercomputers called correlators, immensely powerful machines designed for one Herculean task: to merge the tsunami of data. The correlator's job was to meticulously combine the signals from each pair of telescopes, correcting for the spin of the Earth, the wobble of its axis, and the faint shimmering veil of our own atmosphere that blurs and distorts the light from distant shores of spacetime. It had to align these signals with a precision so extreme, it was like trying to sync watches on opposite sides of the planet to within a fraction of the time it takes light to travel from your nose to your eye. The slightest error, a single miscalculation in the path delay of a radio wave travelling from M87 to 2 different telescopes, would dissolve the entire effort into meaningless static. For months, the correlators churned their processors humming with the strain of weaving together a ghost. What emerged was not a picture, but an even more abstract set of information, a collection of measurements called visibility data. Imagine trying to understand what a vast, intricate sculpture looks like, but you can't see it directly. Instead, all you have are measurements of the shadows it casts when illuminated from thousands of different angles. This is the challenge the EHT imaging teams faced. They had not taken a snapshot. They had meticulously measured the interference patterns created by radio waves from the black hole arriving at different points on Earth. They had the cosmic shadow play, and from it, they had to reconstruct the object that cast it. This is a task so mathematically complex it's known as an ill-posed problem, meaning there isn't one single unique solution. An infinite number of possible images could in theory produce the same data. To navigate this labyrinth of uncertainty, the collaboration employed a brilliant strategy born from the core of the scientific method. They split into 4 independent teams, each isolated from the others. These teams, based in different parts of the world, were given the exact same raw visibility data, but were forbidden from communicating about their results. Each would use different computational algorithms and imaging techniques, different philosophical approaches to filling in the vast gaps in the data left by the empty spaces between the telescope dishes. It was a race, but also a profound test of validation. If these 4 teams, working in a vacuum with their own unique tools, all converged on a similar-looking image, the collaboration could be confident that what they were seeing was a true feature of the universe, not an artifact of their own software or a figment of their shared expectation. It was a way to fight against the most powerful force in science, the human desire to find what you're looking for. The months that followed were a crucible of stress discovery and painstaking cross-examination. Algorithms with names like Chirp and Smiley ground away attempting to build a reliable image from the sparse data points. They operated on a principle of computational parsimony, seeking the simplest, least complex image that was still consistent with all the measurements. They were programmed to be skeptical, to prefer a smooth, uninteresting blur over a sharp, dramatic ring unless the data overwhelmingly demanded it. The scientists would run simulations for weeks, feeding their software test patterns and fake black hole images to see if the programs could correctly reconstruct them. They were debugging their own path to discovery, ensuring their tools were as unbiased as humanly possible. Inside those isolated rooms, digital universes were born and discarded. Was that flicker of brightness a real feature or just noise? Was the dark patch in the center truly empty, or was it a gap in their data they were misinterpreting? Then, in the summer of 2018, the moment of reckoning arrived. The 4 teams came together to finally reveal their results to each other. In a heavily guarded room, one by one, they projected their final images. A hush fell. On the screen, 4 different pictures created by 4 different methods materialized. They were not identical, each had its own subtle variations in brightness and texture, like 4 artists painting the same subject from slightly different perspectives. But the fundamental truth was undeniable and utterly electrifying. Every single one of them showed the same thing: a ring, a lopsided, blazing ring of light brighter on one side than the other, encircling a profound and inescapable darkness. It was a collective, simultaneous gasp of discovery. The relief in the room was palpable, a tidal wave of emotion washing away years of doubt and toil. It was real. The universe had spoken, and for the first time humanity had built an ear large enough to hear its deepest secret. The final image, the one that would be presented to the world, was a carefully calibrated average of these independent results, a composite view representing the most robust and certain features confirmed by all teams. It was a conservative portrait scrubbed of any detail that couldn't be rigorously defended, and yet what remained was one of the most profound images ever captured by human technology. On April 10, 2019, at 6 simultaneous press conferences across the globe, the world held its breath. The screen lit up, and there it was. A circle of fire, a golden halo burning at the precipice of oblivion surrounding a perfect abyss. It was a fuzzy, imperfect donut of light, but it was our first direct visual evidence of a black hole's event horizon. It was the silhouette of a monster, the shadow of M87, cast against the brilliant backdrop of its own incandescent fuel. You could feel the shift in the world's understanding. A black hole was no longer just a mind-bending equation on a blackboard, or a clever animation in a science fiction film. It was a place. A real object with a size and a shape sitting in the heart of a galaxy obeying the laws of physics. The image was a stunning vindication for Einstein, whose theory of general relativity, formulated over a century earlier in a world without computers or space travel, had predicted the existence and the precise size of this shadow with breathtaking accuracy. Based on the mass of M87 Key, which astronomers had estimated by watching the orbits of stars around it, relativity dictated the exact diameter its shadow should have. When the EHT team measured their ring of light, the size matched the prediction perfectly. It was a cosmic bullseye, a triumphant confirmation that Einstein's bizarre, counterintuitive vision of warped spacetime holds true even in the most violent and extreme conditions the universe can muster. But as the initial wave of awe subsided, a deeper, more nuanced understanding of the image began to take shape. For us on our quest for the Photon Ring, this groundbreaking picture was both a monumental victory and a tantalizing clue. What you're seeing in that famous image is not in fact the pure razor-thin photon ring itself. The EHT, for all its planet-spanning power, still had the resolving equivalent of being able to read the date on a quarter in Los Angeles while standing in New York City. It's an incredible feat, but it is not enough to isolate the delicate substructure we're chasing. That thick, glowing band of light is a beautiful, complex blend of several phenomena happening at once. Primarily, it is the direct emission from the accretion disk, the swirling vortex of gas and dust being heated to billions of degrees as it spirals toward its doom. We are seeing the light from the plasma itself, a celestial blowtorch of unimaginable scale. But that historic, breathtaking ring of fire, the first portrait of a ghost. For a moment, humanity simply stood in collective awe. We had done it. We had seen the unseeable, a halo of light framing the edge of forever, and Abyss 6. 5 billion times more massive than our Sun. The triumph of the Event Horizon Telescope was absolute a testament to what we can achieve when we chain continents together to forge a lens the size of a world. But for the scientists who had chased this shadow for decades, the celebration was laced with a profound, tantalizing new hunger. Because that image, as revolutionary as it was, hid a secret far more intricate than it revealed. What we captured was not a single simple structure. It was a beautiful, magnificent blur. Imagine discovering a lost manuscript from a forgotten civilization. The text is revolutionary, promising to unlock the deepest secrets of their world. But the ink has run, the pages are smeared, and multiple texts have been written one on top of the other, their meanings overlapping into a single, almost illegible whole. This is the challenge that faced the EHT collaboration in the wake of their success. The image of M87 is not the Photon Ring. Rather, it is a cosmic palimpsest, a superposition of light from different journeys, each telling a different story about the monster it orbits. To truly understand the black hole, to test the very limits of Einstein's universe, we have to learn to read this smeared ink. We have to unmix the light, We have to layer by painstaking layer unpeel the celestial onion. The outermost thickest and by far the brightest layer of this cosmic onion is what astronomers call direct emission. It's the light that takes the simplest path to our telescopes. This is the raw, untamed glare of the accretion disk itself, the swirling vortex of gas and plasma, being heated to billions of degrees as it spirals towards its doom. The material on the side of the disk spinning towards us is beamed and brightened by relativistic effects, while the side spinning away is dimmed. This is the source of the iconic crescent shape, the asymmetry that proved the black hole was spinning. This direct light, the Photon Ring as it's technically known, is the loudest voice in a cosmic choir. It's a chaotic, thundering roar of astrophysical violence. And while it tells us a great deal about the hellish environment of the disk, its temperature, its density, its magnetic fields, it also acts as a brilliant veil, a curtain of fire. It swamps the more subtle, more profound signals hiding just beneath it, the whispers of space-time itself. To find the true photon ring, we first have to look past this overwhelming glare. We have to learn to listen for the violin playing beneath the symphony of destruction. Beneath that turbulent primary glow lies something far more elegant, something purer. It is the first true echo of the black hole's gravity, the first layer of the onion. This is the light that didn't fly straight towards us. Instead, drawn in by the black hole's immense gravitational pull, it was captured into a temporary fleeting orbit. This light skims past the abyss, completing one extraordinary loop around the black hole before being flung out in our direction. Scientists call this the N-1 subring. Think of it as a gravitational boomerang thrown from the far side of the black hole, swinging all the way around and then flying towards your eye. Because it has travelled a longer, more tortuous path, it carries a much cleaner, more precise memory of the space-time it traversed. Its journey was dictated less by the messy physics of the plasma, and more by the pure, unadulterated geometry of gravity as described by Albert Einstein. This N-1 ring is fundamentally different from the direct emission above it. Theory predicts it should be dramatically thinner, a sharper, more delicate circle of light nested within the broader diffuse glow. It is a direct tracing of the gravitational contour lines of the void. Its precise diameter and shape are not determined by the chaos of the disk, but by the two most fundamental properties of the black hole itself, its mass and its spin. Finding this ring, isolating it from the glare of the direct emission, is the critical next step. It is the first glimpse of the black hole's true gravitational face stripped of its fiery makeup. It is the transition from seeing the weather around the mountain to seeing the shape of the mountain itself. This is the prize the EHT team is chasing now, a sliver of pure geometry hiding within their groundbreaking data. But gravity's looking glass is a hall of mirrors. If light can be coerced into making one pass around the black hole, why not 2, or 3, or 10? And here the mystery deepens into an almost philosophical realm. Hiding beneath the N1 ring there must be another, an N2 subring comprised of photons that have executed 2 full orbits before making their escape. This ring of light would be exponentially thinner still and exponentially fainter, a mere filament of luminescence. It is the echo of an echo, and beneath that an N3 ring from 3 orbits, and an N4 ring. The sequence continues on an infinite progression of ever finer, ever dimmer rings, each one a record of photons that danced ever closer to the event horizon, that spent more time caught in the gravitational waltz before being spun back out into the cosmos. Each layer of the onion we peel back reveals a light that has taken a more extreme, more perilous journey. These higher-order rings are the faint ethereal whispers of the abyss. This infinite stack of rings, each nested within the last, converges on a single perfect razor-thin circle, a line of 0 thickness. This is the photon sphere, the critical curve made manifest. It represents the light that has made an infinite number of orbits, the photons balanced on a gravitational knife's edge between capture and escape. We can never see this infinite ring directly, but its ghostly presence defines the structure of all the rings we can see. It is the fundamental boundary, the mathematical soul of the shadow. The entire series of rings, this incredible nested structure, is the true photon ring. It is a cosmic fingerprint, a barcode imprinted upon light by the very fabric of space-time. And if we could measure it, if we could resolve these individual subrings, we would be holding a Rosetta Stone for gravity. The precise spacing and relative brightness of these rings are predicted with stunning accuracy by the equations of general relativity. Measuring them would not just be a confirmation of the theory, it would be the most precise and stringent test ever devised conducted in a laboratory where gravity is stretched to its breaking point. So how do you find an infinitesimally thin set of rings hidden within a blurry, noisy image? You cannot simply zoom in or increase the contrast. The current resolution of the Event Horizon Telescope is not sharp enough to separate these nested features visually. The rings are smeared together, their light blended into the single thick band we observe. The solution is not in optics, but in mathematics. It is a work of cosmic forensics. Scientists turn to what they know with near certainty, the physics of general relativity. Using supercomputers, they build a library of theoretical black holes. They create thousands of virtual M87s each, with a slightly different mass, a slightly different spin, and a different model for the accretion disk. For each of these virtual black holes, the computers calculate exactly what the stack of photons subring should look like. They generate a precise idealized image of the N00, N1, N2 rings, and so on, all stacked together. Then they simulate what the Event Horizon Telescope, with all its real-world limitations, would see if it looked at that perfect theoretical image. They blur it, add noise, and account for the gaps in their planetary array. The result is a collection of fingerprints, a vast catalogue of blurry rings, each one corresponding to a unique black hole. The final heroic step is to compare this synthetic library to the real data from M87 chaos. They search for a match. It's an act of reverse engineering the cosmos, of finding the one theoretical model out of thousands that, when appropriately blurred, perfectly recreates the image we actually saw. It's like hearing a chord played on a piano and trying to deduce the individual notes by knowing the physics of how a piano works. Early analyses using this very technique have already yielded tantalizing hints, suggesting the faint signature of the N1 ring is indeed present in the data, just waiting for a sharper eye to be teased out. There is another, even more subtle way to hunt for these hidden signals. It involves looking not at the final image, but at the raw data from which it is made. The EHT doesn't take a photograph in the traditional sense. Each pair of telescopes in the array measures a tiny piece of the light wave pattern, a quantity called a visibility. All of these measurements are collected in a complex mathematical landscape known as Fourier space. An image with broad, blurry features like the direct emission from the accretion disk creates a signal that is strong for short baselines telescopes that are close together, but fades away quickly for long baselines. But a sharp, thin feature like a photon subring does something magical. In Fourier space, a thin ring creates a persistent, oscillating, wave-like pattern, like a pure tone that continues to ring out across the entire spectrum. This sinusoidal signature extends far out to the longest baselines, the very baselines that give the EHT its power. So even if the subrings are visually blurred into obscurity in the final image, their unique mathematical fingerprint might be lying there clear as day in the raw data stream. Scientists are now meticulously combing through the petabytes of EHT data, not looking for a picture but for a song. They are searching for the telltale ringing of a pure-lensed photon, a high-frequency note hidden beneath the low-frequency rumble of the accretion disk. It's a search for a pattern woven into the very fabric of the signal. We collected a message from the edge of space-time. But these forensic techniques, as brilliant as they are, can only take us so far. They allow us to infer the presence of the photon ring, but they are not the same as seeing it. To truly unpeel the onion, to resolve the subrings as distinct separate entities, we need a more powerful instrument. We need a sharper eye. This is the driving ambition behind the Next Generation Event Horizon Telescope, or NGEHT. The plan is a massive upgrade to the existing array. It involves adding more than a dozen new radio dishes at new sites around the world, filling in the crucial gaps in our virtual mirror. More dishes mean higher fidelity, creating a more complete and less distorted image. But the most critical upgrade is a move to higher observing frequencies. By tuning the telescope to listen to light with a shorter wavelength, we effectively increase its magnifying power. Higher frequency radio waves are also better at piercing through the cloud of plasma that surrounds the black hole, the very fog that blurs our view. It's the difference between trying to see through a misty morning and waiting for the sun to burn it all away. The Zingy aims to produce not just static images, but high-fidelity movies of the black hole environment. It will be powerful enough to move beyond mere detection and begin the era of precision measurement to finally resolve that first delicate N1 ring around both M87s and the supermassive black hole at the heart of our own galaxy. Yet even this globe-spanning machine has a fundamental limitation. Its maximum resolution is forever capped by the diameter of the Earth. Our planet, which we turned into a telescope, is now the barrier to a clearer view. To take the next leap to resolve the N2 ring and beyond to see the fine structure of gravity's true face, we must transcend our world. We have to go to space. The dream long held by astronomers is to launch one or perhaps several radio telescopes into orbit. A single satellite orbiting the Earth could create baselines thousands of kilometers longer than any possible on the ground. This would provide a quantum leap in angular resolution. It would be like switching from a magnifying glass to a scanning electron microscope. An array of 2 or 3 satellites placed in carefully chosen orbits, perhaps even out at the stable Lagrange points far from Earth, would constitute the ultimate gravitational observatory. Such an instrument, a space EHT, could generate images of M87 with such breathtaking clarity that the individual subrings would pop into view distinct and undeniable. We could watch as matter flares and falls into the black hole and see its light echoed moments later in the first ring and then the second. We could finally see the cosmic hall of mirrors in all its glory. This is the future of black hole astronomy, leaving the Earth behind to get the sharpest possible view of the universe's most extreme objects. And what is the ultimate purpose of this generational quest? Why this relentless drive for a clearer picture? Why chase these ever fainter echoes of a light? Because within the structure of the photon ring lies the ultimate test of our understanding of everything. Each subring, its precise diameter, its exact brightness relative to the others, its subtle deviation from a perfect circle is a prediction made by Einstein's theory. A firm, falsifiable prediction. If we measure the NFL1 and N2 rings and find that their spacing is not what the theory says it should be, then general relativity for all its century of success must be incomplete. Such a discovery would shatter modern physics. It would be the first glimmer of a new, deeper theory of gravity, perhaps a quantum theory that finally unifies the world of the very large with the bizarre rules of the very small. The photon ring is not just an astronomical curiosity. It is a crucible where we can forge our most fundamental laws in the most intense fire the universe can offer. It is a cosmic laboratory built of warped space-time, and its secrets could rewrite our textbooks and reshape our entire conception of reality. The triumph of M87 was not an end. It was a beginning. It gave us the map and showed us where to dig. Now the real work begins, the delicate, painstaking effort to excavate the truth from a beautiful but blurry artifact. The hunt is on, armed with new telescopes and more powerful computers to find those thin, sacred circles of light. But M87, for all its grandeur, is a distant leviathan over 50 million light-years away. Its dynamics play out over weeks and months. There is another target, a creature that offers a different, perhaps even more profound set of challenges. A black hole that is smaller, closer, and far more turbulent. A monster lurking in our own cosmic backyard. The time has come to turn our new Earth-sized eye towards the heart of our own Milky Way to confront the ghost that haunts the center of our galaxy. The hunt for Sagittarius A was about to begin. And so, after decades of theory and years of relentless engineering, the moment arrives. It doesn't come with a thunderous roar, but with a silent, crystalline flood. Across the high deserts of Chile, the volcanic peaks of Hawaii, the ice fields of the South Pole, and now from the silent orbital ballet of new space-based arrays, the signal comes home. Petabytes of data, a torrent of synchronized radio waves captured by a planetary eye, now focused with a precision once thought impossible. This is not the same experiment that first gave us the shadow. This is something more. The Earth-sized telescope has been augmented, its vision sharpened by dishes floating in the void, extending its baseline beyond the physical limits of our world. It can now resolve features not merely on the scale of the black hole's shadow, but within the shadow itself. In quiet rooms across the globe, supercomputers humming with a furious cold logic begin their monumental task. The algorithms refined over a generation of effort are unleashed. They are searching for a ghost, a whisper of light buried within the blazing chaos of the accretion disk. The challenge is almost incomprehensible. The teams are trying to isolate a signal 1,000 times fainter than the bright turbulent plasma it inhabits. It's like trying to hear the hum of a single tuning fork in the heart of a supernova. For months, the digital grind continues a silent war against noise and uncertainty. The data is correlated, cleaned and cross-referenced, every byte scrutinized for the subtle signature they seek. They are looking for a pattern, a coherent structure hidden in the static. False positives flicker and die on their screens, phantoms born of atmospheric distortion or instrumental error. Each one is a small heartbreak, a momentary surge of adrenaline followed by the sober return to the data stream. The process is a digital archaeology patiently brushing away layers of cosmic dust and instrumental noise to reveal the artifact buried beneath. They aren't just creating a picture, they are performing an interrogation of spacetime itself, asking it to confess its deepest secrets. The sheer volume of information is a new kind of ocean, and the scientists are navigators searching for a single legendary coastline. They build complex models of the accretion disk predicting its chaotic light, so that they can peel it away from the data layer by painful layer, hoping that something pure, something fundamental remains underneath. This is the painstaking, unglamorous heart of discovery, a relentless collaborative pursuit of a signal that theory demands must exist, but that nature has hidden with exquisite care. Then, one late night in a processing hub in Germany, a single pixel begins to glow with an unnatural consistency. At first, it is dismissed. Another artifact, another ghost in the machine, but it persists. As more data is folded into the image, the pixel becomes a luminous arc. Another team in Massachusetts running a parallel analysis with different software finds the same feature emerging from their own computational fog like a ship on the horizon. A quiet electric excitement begins to build. Phone calls are made across time zones, voices hushed with a mixture of hope and professional skepticism. They run every diagnostic imaginable, trying to break it to prove it's a mistake. They recalibrate, they reprocess, they try to explain it away with every known astrophysical phenomenon. But the glowing filament refuses to vanish. It holds its form with a geometric purity that defies the chaos surrounding it. It is impossibly thin, unnervingly sharp. As the final layers of noise are stripped away, the arc connects to itself, a perfect, unbroken ring. There, shining with the light of trapped orbits, is the M87 Photon Ring, the last light. The teams gather around their monitors linked by video screens across the planet, a silent global congregation. For a long moment nobody speaks. Tears well in the eyes of physicists who have dedicated their entire careers to this single quest. Decades of abstract equations, of theoretical debate, of engineering struggle, have resolved into this single, luminous circle. It is more than an image. It is a validation, a message from the edge of reality delivered across 65 million years, confirming that we on our small distant world finally understand the language of gravity. To gaze upon it is to witness something entirely new. It is not a physical object, but a path, a gravitational mirage of sublime perfection. It's a circle drawn not with matter, but with the warped fabric of space-time itself. This is the precipice. Every photon trapped in this ring is on a knife's edge, a celestial tightrope walker, performing an eternal unstable dance just above the abyss of the event horizon. The light you are seeing has circled the black hole at least once, perhaps many times, before making a final improbable escape in our direction. It is ancient, delayed, a ghostly echo of the universe that has been held in gravitational stasis, and in its perfect geometry it holds the deepest truths of the monster it encircles. The blazing, messy accretion disk is weather. This thin, elegant ring is the climate. It is the fundamental baseline, the pure signal beneath the noise. The scientists know that they have just been handed a cosmic scalpel of unimaginable sharpness. For the first time, they can separate the physics of the black hole itself from the complex astrophysics of the plasma falling into it. The ring is a direct probe of the gravitational field alone. Its properties are dictated not by temperature or magnetism, but by the pure, unadorned curvature of space-time. They have unlocked a new window, and through it they can now begin to measure the soul of a singularity. The first measurement is the most fundamental mass. For years we have estimated the mass of M87 by observing the orbits of stars and gas clouds. Far from its centre, a reliable but indirect method. The photon ring offers something far more profound. According to general relativity, the size of this ring is directly and rigidly coupled to the black hole's mass. There is no ambiguity, no astrophysical uncertainty. The diameter of that delicate circle of light is a direct readout of the object's gravitational heft. It is the universe's most precise scale. The team measures the angular diameter of the ring down to the micro-arc second. They feed the numbers into the equations Einstein wrote on a blackboard over a century ago. The result that comes back is staggering. They confirm the black hole's mass at 6.5 billion times that of our Sun, but with a precision that dwarfs all previous estimates. The error bars shrink to almost nothing. It is the most accurate weigh-in of a supermassive black hole in history, a feat of measurement akin to determining the exact weight of a cruise ship by measuring the width of a single atom on its bow from 1,000 miles away. The number itself is a triumph, but what it represents is revolutionary. We now have a tool to weigh these cosmic behemoths with an almost godlike certainty, a tool that will allow us to calibrate the growth and evolution of galaxies across the cosmos. This single measurement solidifies our understanding of the cosmic architecture, anchoring our models of galactic dynamics in an unassailable foundation of observational fact. But the ring holds a deeper secret, one that speaks to the awesome violence of the object's nature. It doesn't just tell us how much it weighs, but how fast it is spinning. A non-spinning black hole, a simple Schwarzschild singularity, would present a perfectly uniform photon ring. But M87's, like nearly all black holes, is a spinning behemoth, a Kerr black hole. Its rotation is not merely a feature, it is an active, ongoing assault on the very nature of space and time around it. This spin drags the fabric of space-time along with it, a phenomenon known as frame dragging. Imagine a bowling ball spinning in a vat of honey. The honey closest to the ball is forced to swirl with it. Now imagine that the bowling ball is 6.5 billion solar masses, and the honey is the universe itself. This cosmic vortex has a direct observable effect on the light of the photon ring. The side of the ring, where light is orbiting in the same direction as the black hole's spin, receives a gravitational boost, appearing brighter to our telescopes. The side orbiting against the spin is slightly suppressed, appearing dimmer. The ring, therefore, is not uniformly luminous. It has a bright side and a dim side. This asymmetry is the fingerprint of the black hole's angular momentum. It is a gravitational gyroscope revealing its secrets. By carefully measuring this lopsided brightness, the team can calculate the black hole's spin with breathtaking accuracy. They can see in that uneven glow the evidence of space-time being twisted into a furious, inescapable whirlpool. This is not just a confirmation of frame dragging, it is a full quantitative characterization of it in the most extreme environment possible. We are no longer just theorizing about space-time being dragged by a spinning mass. We are watching it happen. We are seeing the consequences of a cosmic engine so powerful it forces the universe to rotate with it. This measurement allows us to understand the black hole not as a static object but as a dynamic, evolving entity. Its spin is the source of its power, the engine that drives the colossal jets of plasma we see blasting out from its poles at nearly the speed of light. By pinning down the spin, we can finally create complete, accurate models of how these jets are formed and launched, solving a mystery that has puzzled astrophysicists for 50 years. The photon ring has allowed us to connect the black hole's fundamental properties, its mass and its spin, directly to its observable cataclysmic influence on its host galaxy. We are watching the ghost in the machine turn the gears of cosmic evolution. Now comes the ultimate test, the culmination of all this effort. The reason this quest has driven generations of scientists. Does the photon ring match the predictions of Albert Einstein's theory of general relativity perfectly? Or is there a deviation? A slight warp in its shape, a subtle anomaly in its size, a flicker in its brightness that the equations do not predict? This is the moment of truth. For over a century, general relativity has been our guide to the cosmos, passing every test we've thrown at it, from the orbit of Mercury to the detection of gravitational waves. But we have never been able to test it here in this place, on the very last stable orbit of light before the point of no return. This is the strong field limit, the place where gravity is so intense that the theory might finally break down, revealing a deeper, more fundamental reality. Any deviation, no matter how small, would be the discovery of the millennium. It would mean that Einstein's theory is incomplete. It would be the first whisper of a new physics, a quantum theory of gravity, the holy grail that could finally unite our understanding of the very large with the very small. The team takes their hyper-precise measurements of the ring's size, shape and brightness asymmetry, the direct fingerprints of mass and spin, and they place them side by side with the predictions forged by Einstein's field equations. The supercomputers plot the two against each other. The observed data, a set of points shimmering with the light from the edge of time. The theoretical prediction, a clean, unforgiving line drawn by the hand of genius a century ago. On screens around the world, the data points begin to populate the graph. One by one they land, and one by one they fall directly, perfectly, flawlessly upon the line. There is no deviation, no anomaly, no hint of a deeper physics. The photon ring of 87K is exactly the shape and size that general relativity said it would be. The silence in the control rooms is broken not by cheers of triumph, but by a collective audible gasp of awe. The theory holds. In the most extreme gravitational environment we have ever been able to probe, Albert Einstein is still right. There is a strange, profound sense of both disappointment and elation. The dream of finding new physics in this first glance is denied, but the result is perhaps even more staggering. It is a testament to the sheer predictive power of a human idea. A confirmation that a set of equations written with pen on paper can perfectly describe the behavior of light at the edge of oblivion 65 million light-years away. We have pushed our instruments to the absolute limit of what is possible, and all we have found is the triumphant confirmation of our own understanding. The universe in its most violent and exotic corner still plays by the rules we have discovered, but this is not an end. It is a monumental beginning. The confirmation of general relativity to such an astonishing degree of precision is not a closed door. It is the key to 1,000 new ones. We have established a baseline. We have calibrated our most powerful cosmic laboratory. The successful detection and characterization of the photon ring has given us a new tool, a new sense with which to perceive the universe. We can now apply this technique to other black holes like the one at the center of our own galaxy, Sagittarius A. We can begin to compare them to study a population of singularities to see if they all conform so perfectly. And we now know where to look for deviations. This perfect measurement allows us to constrain alternative theories of gravity, ruling out entire classes of ideas that are no longer tenable. We have narrowed the search, clearing the theoretical fog. The quest for a quantum theory of gravity is now more focused, more disciplined, guided by this extraordinary observation. The photon ring has become our standard candle for the abyss, our ruler for measuring the geometry of spacetime itself. And it whispers of even deeper secrets yet to be uncovered. The ring we have just seen, the NL1 ring, is only the brightest. Theory predicts that inside it there should be another fainter ring, an N2 sub-ring made of light that has circled the black hole not once but twice before escaping, and inside that an N3 ring from light that has orbited 3 times, an infinite nested series of luminous circles, each one an echo of the one before it, each one a sharper, more pristine probe of the spacetime geometry closer and closer to the event horizon. These sub-rings are exponentially fainter, exponentially harder to see. They are ghosts of ghosts buried even deeper in the glare. But we know they are there. They are the next coastline on the map, the next peak to be scaled. For within that infinite sequence of rings, within that celestial bullseye, lies the ultimate prize, a complete movie of the black hole's entire visible universe, wrapped around its edge like a film on a reel. If we can develop the technology to see them to resolve these echoes of light, what story will they tell? What new physics might be hiding in their faint, ethereal glow, waiting for an eye sharp enough to see it? We have read the first sentence from the edge of time. Now we must learn to read the entire page. And so we arrive at the edge of the abyss, not in a starship, but through the collected power of human thought. We have followed a ghost, a whisper in the mathematics of a young patent clerk a century ago, a premonition of a place where space and time themselves would surrender. For decades it was a creature of pure theory, a mathematical curiosity confined to blackboards and the dreams of astrophysicists. It was a line of light too thin, too faint, too impossibly close to the maw of infinity to ever be seen. It was the universe telling us this far and no further, but we did not listen. We built a telescope not of glass and mirrors, but of an entire world. We synchronized atomic clocks with a precision that borders on the divine, turning our planet into a single colossal eye. We gathered petabytes of data, a deluge of cosmic information so vast it had to be flown, not wired across continents. We pointed this global observatory at the silent sleeping hearts of distant galaxies at M87 and at our very own Sagittarius A. And we held our collective breath, waiting for the signal to emerge from the noise, waiting for the ghost to finally appear. What we found there shimmering in the reconstructed data was more than just a confirmation of a theory. It was a testament, a monument to that most defining, most noble and most relentless of human traits, curiosity. This ring of light is the culmination of an effort that transcends borders, politics, languages and generations. It is the quiet genius of Einstein, the bold vision of Hawking, the tireless calculations of programmers, the dogged persistence of engineers, and the shared passion of hundreds of scientists from around the globe, all focused on a single infinitesimal point of light. It is a cathedral of reason built not with stone and mortar, but with algorithms, radio waves, and the unyielding conviction that the universe in all its terrifying grandeur is ultimately knowable. To gaze upon the image of the photon ring is to witness a conversation between the universe and ourselves, a dialogue conducted in the language of gravity and light. For so long the universe spoke, and we could only listen indirectly, interpreting the subtle dance of stars or the faint redshift of galaxies. But here in this perfect circle of captured light we have found a place where the universe speaks with stunning clarity. Here the geometry of spacetime is not an abstract concept. It is rendered visible, painted in photons against a canvas of absolute black. It is the universe holding a mirror up to its own most fundamental laws, and we, after 1,000,000 years of staring into the night sky, have finally learned how to look. The journey to this point has been extraordinary, a saga of human ingenuity. But the true significance of this discovery, its real power, is not what it represents as an end, but what it promises as a beginning. We have not merely found a celestial landmark. We have forged a new tool, perhaps the most powerful instrument we have ever conceived for exploring the frontiers of physics. This ring of fire is not just a photograph. It is a cosmic laboratory, a diagnostic screen for the health of spacetime itself. It is a microscope with a lens crafted from pure gravity, allowing us to zoom in on the very fabric of reality at its most extreme. Until now, our tests of general relativity have been magnificent, but they have all been conducted in the gentle, placid waters of the cosmos. We have seen starlight bend around our sun. We have detected the subtle, spiraling decay of binary pulsars. We have even heard the faint chirp of gravitational waves from merging black holes 1 billion light-years away. But all of these are mere ripples on the surface of spacetime. The photon ring is a glimpse into the maelstrom. It is a place where spacetime is not gently curved, but violently torn, twisted and dragged into a vortex of unimaginable intensity. Here, in this ultimate crucible, Einstein's beautiful equations are subjected to a trial by fire unlike any other. Every single photon that comprises that ring is an exquisitely sensitive probe. Its path, its energy, its polarization all carry a detailed report of the gravitational field it has just barely survived. The precise shape of the ring, its exact diameter, tells us the black hole's mass, with a certainty that will recalibrate our understanding of galactic evolution. But it is the subtle imperfections we will search for that hold the key. Is the ring perfectly circular as theory predicts, or does it exhibit a slight lopsidedness, a minute deformation that encodes the ferocious spin of the black hole, the frame-dragging effect that twists space itself into a cosmic gyroscope? By studying how the brightness varies around the ring, we can map the magnetic fields and the turbulent plasma swirling at the precipice, watching matter's last desperate cry before it is extinguished from our observable universe. General relativity makes a very bold and simple prediction about black holes, what physicists call the no-hair theorem. It states that a black hole, once it settles down, can be described by only 3 properties: its mass, its spin, and its electric charge. All other information, all the complexity of the matter that formed it, whether it was made from stars, planets, or cosmic dust, is erased. A black hole in this view is the simplest object in the universe. The The photon ring is our ultimate test of this profound idea. If Einstein is perfectly correct, the ring will have a specific rigid geometry defined only by that mass and spin. Any deviation, any unexpected bump, wobble, or distortion, no matter how small, would be a seismic event in the world of physics. It would be the first crack in the foundations of general relativity, a signpost pointing toward a deeper, more complete theory of gravity. We are no longer just looking at a black hole. We are performing a biopsy on the tissue of spacetime, searching for the telltale signs of new physics. And it is here in this quest for a new physics that the photon ring transitions from a powerful tool into a gateway to an entirely new reality. For a century, we have lived with a deep and unsettling chasm running through the heart of modern science. On one side, we have general relativity, the majestic theory of the very large governing planets, stars, and the grand architecture of the cosmos. On the other, we have quantum mechanics, the strange and ghostly theory of the very small ruling the world of atoms and subatomic particles. Both theories are fantastically successful in their own domains, yet they refuse to speak the same language. They are fundamentally incompatible. Finding a unified theory, a theory of quantum gravity, that can bridge this gap is the single greatest challenge in all of physics. To solve it, we need a place where both theories are forced to apply. We need a place where gravity is so colossally strong that its quantum nature, normally hidden from view, might finally be revealed. We need, in other words, the edge of a black hole. The photon ring is our observation deck, our window into this quantum realm. What will we see when our telescopes become sharp enough? If space-time, like everything else in the quantum world, is ultimately granular, made of discrete indivisible units, like pixels on a screen, then perhaps the photon ring will not be a perfectly smooth, continuous curve. Perhaps under the ultimate magnification, it will appear subtly fuzzy, or its light will show faint shimmering fluctuations, the signature of spacetime's quantum foam bubbling at the event horizon. Could it be that the light is not perfectly trapped in a single orbit, but exists in a quantum superposition of many possible paths, a ghostly echo chamber of possibilities that we could one day measure? These are no longer questions for science fiction. They are concrete, testable hypotheses that we can now address. The photon ring provides the experimental data, the ground truth that can guide our theorists through the bewildering mathematical jungle of string theory, loop quantum gravity, and other candidate theories. This ring is not just a boundary in space, it is the boundary of our ignorance. Beyond testing our existing theories, this celestial artifact beckons us to imagine what other secrets it might hold. What if the darkness inside the ring is not entirely empty? Our models of the universe suggest that the vast majority of matter is not the familiar stuff of stars and planets, but an invisible, mysterious substance we call dark matter. Galaxies seem to be embedded in vast halos of this material. Could a dense clump of dark matter be orbiting the supermassive black hole, too diffuse and dark to see directly? Its gravity would leave an unmistakable fingerprint, subtly warping the path of the photons as they circle the abyss, imprinting a faint shadow or a distortion on one side of the ring. Seeing such a signature would be our first direct gravitational glimpse of this elusive substance, confirming its existence and constraining its properties. Or perhaps we might find something even more exotic. Some theories predict the existence of ultralight particles like axions, which could form vast oscillating clouds around a spinning black hole through a process called superradiance. Such a cloud, a gravitational atom the size of a solar system, would bleed energy away from the black hole's spin, and its ghostly presence would leave a very specific periodic signal in the structure of the photon ring. To find such a thing would be to discover a new fundamental force, a new piece in the grand puzzle of the cosmos. The photon ring acts as a cosmic net capable of catching the faintest gravitational traces of particles and fields we never knew existed. It allows us to go on an astronomical safari hunting for the universe's most bizarre and elusive creatures in their natural habitat. And the mysteries only deepen from there. The photon ring is inextricably linked to one of the most profound paradoxes in all of science, the information paradox. Quantum mechanics insists that information can never be truly destroyed. Yet if you throw a book into a black hole, general relativity suggests its information, the words, the ideas, the story is lost forever, sealed away behind the event horizon. This is a fundamental contradiction. For decades, physicists have argued about the solution. Does the information somehow escape, perhaps encoded in the faint Hawking radiation that black holes are predicted to emit? Or is there some new physics at the event horizon itself? The photons of the ring are our most intimate witnesses to this boundary. They skim the horizon, interacting with the violently curved space-time and the quantum vacuum for billions of years before escaping to our telescopes. Could they carry with them a subtle imprint, a quantum scar from the processes happening at the very surface of the black hole? Could they hold a clue encoded in their quantum state that would help us resolve this paradox and rewrite our understanding of information entropy and the nature of reality itself? We are listening to the whispers from a cosmic prison wall, hoping to learn the fate of its inmates. Ultimately, this shimmering circle of light forces us to confront our place in the universe with a new and humbling clarity. We live our lives on a scale of meters and seconds on a gentle planet orbiting a placid star in a quiet suburb of the Milky Way. The universe of the Photon Ring is a place of extremes so profound they defy our intuition and strain the limits of our language. It is a place where a single second for a circling photon can correspond to millennia for us. It is a place where space flows faster than light and the future becomes an inescapable physical direction. It is a place where all our notions of location of time of existence are stripped down to their absolute mathematical essence. To study the photon ring is to engage with the universe on its own terms. It is to accept that the cosmos is far stranger, more beautiful and more terrifying than our ancestors ever imagined. But it is also to affirm that the human mind, through the tools of science, reason and collaboration, is capable of reaching out and touching these alien shores. We have captured the light from the edge of time. We have photographed the silhouette of infinity. What was once the domain of poets and philosophers is now the domain of observation and measurement. So look once more at this impossible object. See it not as an image of an ending, not as the universe's final stop sign. See it for what it truly is, a beacon. It is a lantern in the deepest, darkest forest of the cosmos, and its light does not warn us away. It illuminates the path forward. It shows us where the next great questions lie buried. It challenges us to build better telescopes, to devise smarter algorithms, to ask bolder questions, and to continue the journey. The photon ring is not the last light you see before a black hole. It is the first light of a new dawn in our exploration of the universe. It is the brilliant, unending dawn of discovery.